So in lesson 24, the first part, we did the 24A and B. You're going to see I moved, there was a problem in here, and I moved it because it really should come after we talk about molar solubility. So molar solubility is S. When we did acid-base equilibrium and ice tables and all of that, we had X, which was for molarity. So now we're going to have S, which is going to tell us something about molar solubility, but really X and S are essentially going to play the same role, if that makes sense. So the first part says to define molar solubility, which has units of this, and solubility, which have units of that. So molar solubility is going to be the amount of moles of a compound that dissolves in 1 liter of solution, usually aqueous. Now the other one is solubility. Solubility, on the other hand, is going to be the amount of grams of a compound that dissolves in 1 liter of solution. So the only difference here, the key word is moles and grams. So because molar solubility has units of m, we said earlier that it's essentially the same thing as X on the ice table, but we're going to use that for acids and bases that we talked about in the last chapter. We're going to use S's when we start talking about molar solubility. So the first part of this question says to calculate the molar solubility and the solubility of lead sulfide. So to start off with, remember it's always going to be starting off with the solid, breaking apart into its individual ions. Now lead has multiple oxidation states, but this Roman numeral reminds me that this should be a 2+. And we know that sulfide is in group 6A, so that's the 2-, same as oxygen. And so this is our balanced chemical equation. I'm going to write my ice table beneath that. Just like water didn't count, solids are not going to count. And I'm not told anything about initially at all. But I know that this solid is going to dissolve in some respect, some amount, to produce a certain amount of lead and sulfide, but I just don't know how much. So I start off with 0. It's going to change by a factor of +S because I'm adding this into solution and forming the aqueous ions. So the reaction will shift to the right. I am theoretically consuming the lead sulfide. However, don't have to worry about it because it's a solid. It's not going to show up in the expression. So now I'm going to plug this into KSP with products over reactants. I'm going to plug in the S value, which is going to be S times S, which comes down to be S squared. And if I go up to the top, I can look up my lead sulfide value because of alphabetical order. And the KSP is 3.4 times 10 to the negative 28th. So it's a very small number, meaning it's not going to want to form a whole lot of aqueous ions. Okay, so now I'm going to take the square root of both sides, and what this is going to tell me is that S is equal to 1.84 times 10 to the negative 14th, and the units on this are moles per liter. So this is the molar solubility, this answer right here. But the question that asks me to go ahead and solve for the solubility, which is grams per liter. So now I'm going to take this up here, and I'm going to use the molecular weight of lead sulfide, which is 239.3. grams per mole. So that's just straight off the periodic table. It has been a while since we've done that math. And what that's going to give me is 4.4 times 10 to the negative 12th grams per liter. And that is going to be the second answer. All right. So what I want you to do is pause it here and try to set up your equation. So hopefully you're back now and you have got this set up. If you didn't set it up, please listen to me, even though we're not together and you think I may not know. I think it's still going to be best for you to practice setting this up without me. That's what I would make you do if you were in class. So this is my equation that I get. And lead still has a 2+ charge. Iodine is group 7A, so it's got a 1- charge. And so my balanced chemical equation is going to have a 2 coefficient in front of the lead. And so I want you to pause it here and set up your ice table. What do you think those values should be? Okay, if you haven't paused it, I recommend it. My son is learning how bossy I am as a teacher by being home with me, but yet he insists that he loves being homeschooled by me. So you may remember we talked about how the 2 coefficients impact our ice tables. Okay, so if you didn't catch the 2, this is a reminder that that's there. Now, take a moment, set up your KSP expression. Pause it here. Test to see if you can set up the KSP, products over reactants, correctly. Okay, hopefully you paused it. And hopefully while you had it paused and you figured it out yourself, you determined that this was the KSP expression. And now I'm going to plug everything in. KSP is equal to S times 2S squared. So what that means is the KSP is then equal to the S, and remember the square is going to square the 2 and the S, so this becomes 4S squared. And because the KSP is S times 4S squared, this becomes 4S cubed. I need to go up and look for my KSP for lead iodine, 1.4 times 10 to the negative 8th. So it kind of favors products more. Now to work out the problem, I'm going to divide by 4. And then the other part is to take the cubed root. Okay, so you're going to divide by 4 and take the cubed root. On your calculator, let me write the answer out first. S is going to be 0.00152 moles per liter. So that is going to be the molar solubility. Now on your calculator, when you get ready to do the cubed root, if you don't know how to find your cubed root function, that's okay. You can do the caret and do 1 over 3. So it's just like you do the exponents when you have like to the 4th power. But if you do 1 over 3, that will take the cubed root. And you can do 1 over 4, 1 over 5. And so it's a pretty easy way if you can't find the cube function. The last part is to convert that to solubility using the molar mass. And that's going to give me pretty large number compared to the last one. I wrote a infinity. Okay. All right. So not too difficult because we're just using ice tables just like we had before. And pretty simple stuff, I guess, comparatively speaking.